Okay, next we're going to talk about arc length. So there's two types of arc length that we need to deal with, and there's a few formulas that it can look like. So we'll just talk about a couple of those pretty quickly, and then just do a quick example, and then we'll move on. Because this particular concept isn't super complicated, but it is really important for a lot of the line integrals we're going to be doing here in the next unit or two. So the first thing we need to talk about is that you can do arc length both as a length or as a time. So you can parameterize your arc length as a function of time or as a function of length. So we'll do both of those. We'll talk about it a little bit, and then we're going to move on. So just to start with, arc length is going to be defined as the integral from a to b of the square root of each component as a derivative squared and summed. So g prime of t squared, f prime of t squared, and h prime of t squared. Okay, and all of that's of course going to be integral with respect to dt. So this is one of the forms. There's another form though which is a little bit more compact and a little bit easier to write. So we have integral from a to b of the square root of r prime of t as a vector dot product with r vector prime of t. And then that's still with dt. Now if you think about this just for a second, you'll notice that these are the exact same, because when you do the dot product, you take the x component times the x component, and the y component times the y component, and the z component times the z component, and you add them all together. So that's exactly what we have here. So we're good either way, totally equivalent. And then there's a third way that's even shorter, and that is going to be that the arc length is actually just the integral of the magnitude of velocity. Now, this is more of a physics context, so we're not going to really use that very much for what we're talking about, but if you ever see this integral, that is still arc length as well. You can calculate it this way, you can calculate it this way, it'll work out the exact same. Okay, so let's go ahead and go into this first example, and then we'll take an aside to talk about how to parameterize the arc length differently, and then we're going to be pretty much done. So we're going to start with a vector r of t that's equal to a cosine of t, a sine of t, and c of t. So remember, a and c are both constants. So the first thing we're going to do here is we're just going to take our derivative, because like we saw in our formula, we need to do the dot product of the derivative squared. So our derivative here is going to be negative a of sine of t, and then we have positive a cosine t, and we just have c, right? And so now what we can do, I'm going to use the dot product way, so we're going to do r prime of t dot r prime of t. Okay, so then I'm just going to get negative a sine of t squared plus a cosine of t squared and plus c squared. So we're going to here we're going to get a squared plus a squared, sine squared, cosine squared. So sine and cosine are just going to be 1. So we're going to get a squared here plus c squared equals our r prime of t dot r prime of t. Okay, that looked not very good. There we go. Okay, so the next thing we're going to want to do here is talk about how we can parameterize this into, we need to finish calculating our arc length. So let's do that first. So arc length is usually written as s of t, and that in this case is going to be the integral from 0 to t, and then you have your square root of a squared plus c squared d tau. So we use d tau here because we want to use t as our upper bound, because what we're going to do is after this we're going to parameterize it into a function t of s. Normally if you weren't doing that, you would just be given an a and a b to go through, or you would take an indefinite integral. But in this case, because I'm trying to do two things at once, that's why we're doing this tau and t thing. So there's no taus or t's inside the square root, so this is just one big constant. So nothing's going to change there. So we're just going to get t square root of a squared plus c squared, right? And that's just going to be the whole thing. And there's no plus c because we did have bounds, so we don't need to do a constant. The 0 just cancels out when you plug it into your t, so we don't have to worry about that one either, or when you plug it into your tau. Okay, now, so this is, all of this stuff is s of t. So to parameterize this, instead of being arc length as a function of time, we want it to be time as a function of arc length. Instead of writing s of t, we're going to rewrite this, as s equals t of s, and then everything else is the same for now. Okay, and so then this seems pretty straightforward. All we have to do is just isolate for t of s. So we got t of s is equal to s over square root of a squared plus c squared, right? Now we're not quite done yet, right? So we've now written time as a function of arc length, but now we need to go back and plug this back into our original vector. So now we're going to have r of t of s, and that's going to equal, we're literally everywhere we had a t in our original vector, we're going to plug in our s. So we're going to have a cosine, and there was a t here, so now we're going to plug in s over root a squared plus c squared. And then we're going to have a sine of the same thing. So we have s over root a squared plus c squared. That's not the best. Let me clean that up real quick. That's still not a whole lot better. Writing like right over a crack in the screen. Okay, and then our last one we have c times the same thing. S over square root a squared plus c squared, right? And then make sure to finish your vector notation. And that's it. So we have now gone all the way from the very beginning where we talked about just what arc length is. We took a vector valued function, found the arc length of it with respect to time, and then we actually changed that and found the time with respect to arc length and plugged that back into our vector. So now we have our entire vector valued function with respect to arc length instead of with respect to time.